Hello everyone. In this lesson we're going to quickly recap the nature of roots and include the case where you might have complex roots. So if I ask the question, how many zeros can a quadratic have? So what are the different cases for a quadratic? And if this works for a quadratic, by the way, it would work for other graphs that would also have roots. So we're just using quadratics because it's the one that's, easiest one to visualize. So if I draw a parabola here, so this parabola right now has two roots because it is crossing the x-axis at two different spots. However, if I move that parabola up, and I can put it anywhere along the x-axis, now it's only touching the x-axis at one point, and therefore it only has one root. And if I move it even higher, at that point it has no roots, and this is the case where we would say that it actually has complex roots, and we'll have to investigate that a little bit further. So a quadratic can have three different cases. So I'm going to draw these out here, and then we'll continue. So as you can see here, I drew out the three different cases. We've already discussed two roots. Here is one root, and I decided to draw the parabola upside down because we have a tendency to always draw parabolas as the smile shape or opening up, but you can have parabolas that are facing or opening down like this. Doesn't matter, it still only has one root. And then this one here, which has been moved up over the x-axis, has no roots, but we say that this actually has complex roots. So that's important to note in higher level math classes, that even if it looks like a parabola doesn't have roots, it still does have complex roots. And if we've seen imaginary and complex numbers at this point, you'll see what I mean by that in a second. So let's go look at a couple of examples, 3 to be precise. So how do you know the nature of roots? Now, if a parabola, or a quadratic I should say, is factorable, you can factor it pretty easily usually and find the zeros. But if, and I mean the general case is that quadratics may not be factorable, and the more you look at real world scenarios, the more you're going to end up with numbers that aren't going to be nice to work with. Luckily, we have the quadratic formula, and inside the quadratic formula there's a very important part to it. So the quadratic formula allows us to find zeros by filling in this equation, and I'm going to change colors for the part under the root here. So minus b plus or minus the square root of b squared minus 4ac over 2a. In a previous lesson I actually proved that, and that's for any quadratic that has this form. Okay, now the green part, the b squared minus 4ac, is called the discriminant. And the discriminant is an extremely important part of this equation because it's under a square root. And because it's under a square root, if you ended up with a negative number under the root, you can't square root a negative number unless you go into the complex domain. So whether the root is a specific value is going to determine the nature of the roots. So the first one we're going to investigate is what happens if the square root value isn't negative, but is actually a number that you can square root, okay? And that's what we're going to look at with this first example here. So if you look at this first example, if you tried to factor it, so two numbers that multiply to negative 4 and add to 11, that doesn't work because negative 4 only has 2 and 2 and 1 and 4 as its factors, so we can't actually factor this one using that technique. But we can use the discriminant to find out how many zeros we're supposed to have. So the a is the coefficient in front of the x squared, the b is the coefficient in front of the 11, and the c is the negative 4. Please do not use the x's. The x's are not coefficients, they are variables. We are only using the coefficients in front of the terms, okay? So this would become 11 squared minus 4 times 1 times negative 4. Now, there's a trick here that I'm going to introduce right away. If you have a minus sign here, and any of these values, only one of them is negative, that means that you're always going to have a positive on this side of the expression, because this negative and the one negative from one of these two variables is going to cancel out and become a positive. That means your answer has to be positive, all right? And that's one of the cases. So just to prove that to you, let's use a calculator here and calculate what that value is. I'll just do it off screen. That's giving 137. This is a positive answer. And when you get a positive answer, that means you're going to have two real roots. And here's why. Let's actually put all of the values into the quadratic formula now. So we're finding our zeros with the quadratic formula. It's up here, so I'm not going to rewrite it. So minus b, b is 11, so negative b, plus or minus the square root of 137, which we just calculated as our discriminant. So it's never a waste of time to do this calculation, because you need that value anyway if you're going to be calculating the roots. Divided by 2a, a is 1. So 2 times 1 goes underneath here. And what's going to happen is this is going to give us two answers. We're going to get negative 11 plus the square root of 137 over 2, and negative 11 minus the square root of 137 over 2. And there are your two real roots. Because we can square root 137, now we're not going to, because that's going to give us a really ugly decimal, all right? And the higher you go, the less you want to work with decimals. So this is considered a perfect answer. We're going to leave it like that. One thing you could check is the square root value here, the 137, is it containing a square rootable number? Now, I don't think it is, and I really don't want to check right now. So, but you could try to simplify it if there was something that you could see that was square rootable inside of 137. But these are our two real roots. These are two real numbers. You can actually plot them on a graph. They're not pretty, but they are real numbers. Now here's another example, and you can see right away that this one is not factorable because we have these really ugly decimals involved. Let's see what happens when we do our discriminant for this one. So again, b squared minus 4ac. B squared is negative 147.42 squared minus 4 times a, which is 13, times c, which is 417.936. Now, I'm hoping you can see in this case that, well, there's a couple of things that are happening. First of all, your b is a negative value, but you are going to be squaring it, and anytime you square a negative value, it becomes positive, right? For this part, this time I don't have a negative value in one of the two brackets. So when I multiply negative 4 times whatever's here, I'm going to end up with a negative term here. So I'm subtracting a number from another number, and as soon as you're subtracting a number from another number, there is the chance of getting a negative value. So this is why you could end up with a negative under the root. Now let's see what happens with this one. So I'm just going to pull out my calculator here and do the calculation. So I just realized there's a slight mistake in my calculations here, so I'm just going to fix that. This is supposed to be 9.357, and if I don't have the perfect answer here, it had rounded it off on my previous calculation. I apologize for that, but I'll just fix it really quickly here. So if we do bracket 147.42 negative squared. Now, you don't actually have to include the negative because you know that the square is going to get rid of it anyway, but I'm just including it here so you can see what's happening. Minus 4 times 13 times 417.9357. And look at the answer we end up here with. We end up with a 0. If you end up with a 0, what does that mean for how many roots you're going to have? Well, it means you're only going to have one root. Your parabola is touching the x-axis at the vertex. Now, how can we know that? Well, if you actually calculate your zeros with the quadratic formula, so minus b, so b is negative here, so I'm just going to write it out as minus negative, but you know that that's going to become a plus. So you could skip that step in your head and just change it into a plus. Plus or minus the square root of 0. And this is the key point right here. And that's all divided by 2a. So 2 times 13 is 26. Because I have a plus or minus root 0, the root of 0 is just 0. So even if I added 0 or subtracted 0, I'm going to get the exact same answer either way. So you can just simplify this to 147.42 divided by 26, and that would be your only x value where the parabola touches the x-axis. So it's touching the x-axis at only one point. And you could divide this if you needed to find out what exactly that point was. Okay? So we've now seen an example of what happens if you have a positive number for your discriminant, what happens if you have 0 for your discriminant, and the last one is what happens if your discriminant is negative. So here's the last example. Let's calculate our discriminant. We're going to get b squared, which is negative 30 squared, minus 4 times a times c. Now, in this case, we have 3 things multiplying. All 3 of them are negative. So that means you're going to get a negative times a negative, which is a positive, times a negative, which is a negative. So you're going to be subtracting something from something else. And every time that happens, there is the possibility of getting either 0 as your answer or a negative root. So I'm just going to calculate this off screen here. So 30 squared minus 4 times negative 5 times negative 52. And this ends up giving negative 140. So we now know that we're going to get 2 complex roots. Normally in grade 10 or earlier lessons when you're learning about this, you would have said there are no roots, okay? But in the higher level classes, you have to state that this is going to be 2 complex roots. Let's put it into the quadratic formula and see how that works. So my zeros minus b, which would be 30. So I'm going to skip the step of putting the minus negative there. I can see that the b is negative 30, so it's going to be minus negative 30, which is plus 30, plus or minus the square root of negative 140, all divided by 2a. A is negative 5, so this becomes negative 10. So what are we going to do with the square root of negative 40? Well, we're going to treat it as a complex number, which means changing the negative 1 into an I squared. And once you've done that, you can now split it up into your 2 answers. Now 140, it's 14 times 10. I'm just trying to think if 140 is square rootable. 14 times 10, that would be, there'd be 2 2's in there. 2 times 7 times 2 times 5. And I believe, so that would be 4 times 35. And then 35 doesn't contain anything square rootable, but I can definitely take out a 4. Okay, so this is the square root of 4 times 35, 140. I think I did that right. Anyway, that's just a side note. We're really dealing with the complex nature of things here, but we really should try to simplify our roots. So we're going to have 30 plus square root of 4 is 2. The square root of I squared is I. And then root 35 is going to be left in there, all divided by negative 10. And then we're going to have 30 minus 2I root 35 divided by negative 10. Now you should never leave a negative in the denominator of a fraction, and there's two things here. We could put it in front of the entire fraction, or we could join it to the numerator at the top. I'm just going to move it in front of the entire fraction here. Otherwise it would be negative 30 minus 2I over root 35. And those are our two complex roots. So in summary, we have three cases. If b squared minus 4ac is greater than 0, this gives two real roots. If b squared minus 4ac equals 0, we get one real root. And if b squared minus 4ac is smaller than 0, we get two complex roots. And this is what's called the nature of roots. So that's going to complete that lesson. Have a great day, everybody.